We're surrounded by smart machines, right? From the phone in your pocket to the robots that build our cars. But what actually makes a machine smart? Today, we're going to pull back the curtain on the huge revolution that's making our world more connected and intelligent than ever before.
I mean, seriously, have you ever seen one and just wondered, how does it know what to do? How does it know precisely when to weld, or exactly where to move, or how to pick up that one specific part from a conveyor belt? It kind of looks like magic, doesn't it? Well, spoiler alert, it's not. The answer is actually part of a massive global shift. That robot, it's just one tiny piece of a much, much bigger puzzle. We're talking about a revolution that's transforming entire industries, not just what happens on the factory floor.
And that revolution is called Industry 4.0. It's literally the fourth major shakeup in how we make things. You know, we went from steam power to electricity and mass production, then to computers and automation, and now we're in the age of data and smart technology, where things like the Internet of Things and cyber-physical systems are creating truly smart factories.
Okay, so for any machine to be smart, it first needs to be able to do what we do, sense the world around it. Think of it like giving the factory eyes and ears. This is where it all begins.
Get ready for this number, 50 billion. That is the staggering number of connected sensors that are already out there, deployed across the globe. And for every new IoT device that comes online, it brings an average of 4 new sensors with it. The scale is just mind-blowing.
At the very heart of Industry 4.0 are these IoT sensors, and the best way to think about them is as the digital nervous system of a modern factory. Seriously, they're gathering all this data from the physical world, temperature, pressure, position, vibration, and they're turning it into digital signals that machines can actually understand.
And you know, we're not talking about some small niche technology here. The market for these sensors is already massive, over $10 billion, and it is just exploding. That growth is the economic engine that's pushing this whole smart machine revolution forward.
And of course, the technology itself is not standing still. It's evolving super fast. Right now, we're seeing 5 key trends. Sensors are getting way smarter with AI. They're becoming more power efficient. We're seeing new soft and virtual sensors. And then there are huge innovations in something called sensor fusion and in biosensors. So let's dig into that first trend, smarter sensors. It used to be that a sensor would just pass raw data along to be processed somewhere else. But now, smart sensors can actually process that information right there on the device itself. They're essentially becoming tiny little computers, what we call edge devices. A perfect real-world example is something like Amazon's Ring glass break sensor. It uses AI to listen for the very specific sound of a window smashing. The decision, hey, is this a break-in, is made instantly, right there on the sensor. That's way faster and more secure than sending a big audio file to the cloud to be analyzed.
Next up is sensor fusion, and the idea here is pretty simple. Multiple sensors working together are way better than one. It's like having multiple human senses. By combining data from different types of sensors, say a camera, LiDAR, and radar, a system can build a much richer and much more reliable picture of its surroundings.
And this isn't just a neat idea. It's absolutely critical. As the CEO of Mobileye points out, for something as complex as a self-driving car, you can't just slap a bunch of parts together and hope for the best. The sensors must work as a single, integrated system to be safe and effective. Okay, so we have the senses, and they're collecting all this rich data. But that information is totally useless unless the machine can actually act on it. So, how do we turn data into physical motion?
The answer is a fascinating field called mechatronics. It's not just mechanics and it's not just electronics. It's the seamless combination of mechanics, electronics, automation, and computing all working together to create a single optimized system.
This visualizes the whole feedback loop perfectly. The sensors provide the input, a digital control system, like a little computer brain, processes that input, and then actuators, things like motors or hydraulics, produce the physical action. It's just a constant cycle of sense, think, and act. So we have the senses and we have the muscles. But these systems are incredibly complex. How do engineers even begin to design and build them without everything falling apart into a total mess?
Well, to manage that staggering complexity, engineers don't just wing it. They rely on established blueprints, standardized models from the world of systems engineering that give them a roadmap to get from concept to reality.
A classic blueprint for this is the V model. It's a really disciplined process. You start at the top with a big idea. You break it down into smaller and smaller design components as you go down the left side of the V. Once you get to the most detailed level,
You build your way back up the right side, testing and integrating at each step to make sure the final product perfectly matches those original requirements. So if the V model tells you how to build it step by step, the RAMI 4.0 model is the architectural map that shows you what you're building. It's like a universal 3D framework for Industry 4.0, making sure that every component from every company, from a physical sensor to a business software, can speak the same language and fit together perfectly. But even with the best blueprint in the world, engineering in the real world isn't about perfection. It's about making smart compromises. It's a constant, delicate balancing act. First, you've got the classic trade-off between cost and performance. Sure, you want a more precise motor, but that means a more expensive controller. You can try to optimize software to squeeze more out of cheaper parts, but at some point, higher performance just costs more. The exact same tension exists between size and performance. We all want smaller, sleeker devices. But a smaller device has less room for a powerful battery, and high-performance chips generate a lot of heat that needs to escape, so shrinking a design can directly impact its capabilities. Beyond all those physical constraints, engineers are constantly managing risk. Using tools like this risk matrix, they weigh the likelihood of a failure against its consequences. A small, unlikely problem might be okay, but anything in that top right red corner, a likely problem with severe consequences, that has to be designed out of the system, period.
So, what does this all mean when we put it all together? Well, what we see is a future that is completely and totally integrated.
This whole smart machine revolution really rests on three core pillars. First, the senses, billions of IoT sensors gathering data. Second, the muscles, the mechatronics systems that turn that data into action. And third, the blueprint, the engineering models that let us build these incredibly complex systems reliably. And this brings us to a final, really crucial question. This technology is moving way beyond the factory floor. It's going into our homes, our cars, and our cities. So as every object around us becomes intelligent and interconnected, what kind of new possibilities is that going to unlock? And, just as important, what new challenges will we have to solve?